Well, first, I'll start off with the in-class people. In-class people, take out your phones. It's turned off, turn it on. Virtual people, I guess, do the same. Take out your phones. And who has the YouTube app? You have the YouTube app? Kyle already asked you. YouTube, do you have the YouTube app? All right, so same with the virtual people. If you have the YouTube app, this is what I want you to do. And I just checked it with Kyle here. So open up the YouTube app. Where'd it go? Open up the YouTube app. You should see your picture in the top right. You click on your picture in the top right of the YouTube app. It should say time watched. I want you to click on that. So for everyone, if you're virtual or if you're in class, go to time watched. So who here found it? You're there, you're there, you're there. Okay, virtual people, I'm hoping you're there as well. So again, YouTube app, click on your picture in the top right, click on time watched. What we're going to do, so you should see something, a minute daily average. And that's the number that I'm going to utilize here. So that blank minute daily average, that's the number we're going to use to determine how frequently Southeastern students watch YouTube. And this is what I want you to do with that number. So mine, so I watch a considerable amount of YouTube. So mine is 3 hours and 27 minutes. But I don't want that number. I want 3. So if you take out your calculator, we're going to quickly convert this to a decimal. I want 3 plus 27 over 60. We're going to convert that to a decimal. So that's the number I want. And that will give us the decimal version, 3.45. That will be the number of hours. Because remember, there's not 100 minutes in an hour, there's 60, so we have to convert that. The ratio would tell us the true decimal. So whatever the minutes is, if there's no minutes, then you just keep the hours. And that's the number I want. So go ahead and figure out your number right fast. I'll give you all a few minutes. If you don't have the YouTube app, well, there is another way you can look at it using your battery settings on your iPhone, but I don't think I'm too familiar. I'm not too familiar with iPhones. I'm just hoping to get a good amount of data values that we can work with here. So if you already figured out your number, if you're virtual, go ahead and type it. If you're in class, I'm going to start writing those out off to the side here. So mine was 3.45. Did anyone figure out their number yet? 0? 0?
That's 37. Are you talking about daily average?
The daily average.
5.
So what was yours?
5.
5?
Yes.
Mine was 1.22.
1.27?
22.
27?
22.
Oh, 20, I'm sorry. 22. Kyle, what was yours?
0.87.
0.87. Okay, let's start writing down everybody. Okay, perfect. This will be awesome. And good to know I'm the outlier. Awesome. I watch a lot of YouTube.
Watch sports.
Yeah,
First day.
I watch a lot of football stuff. All the football commentators. I watch a lot of them. Let's see, 0.52. Okay, so let's go ahead and write down all these. 0.58, 2.330, 3.17, 0, 3.1, 0. 0.55, 0.23, 3.22, 5.28, 1.7. That seems to be it. Okay, cool. So enlarge that, bring this back. Let's clean this up a little bit. Okay, so we got a considerable amount of data we can work with. So let's see. 3.45, a 0, a 0, 5, 2, 0, 5. I think that was 1.22, 0.87.
Is that bottom one 5.47?
5.27. I'm just rewriting them. It always.
Yeah, you're good. I just couldn't see it.
2.33, which is 0. So let's just clean this up a little bit. 0. Okay. 3.17, a 0. 3.1, 0. 0.55. 0.23. Takes care of those and that one. And we have a new outlier. I'm surprised mine isn't higher. I normally fall asleep with my YouTube on. But in any case, here's some data we have to work with. Curious how these zeros are going to play into all of this. But what we're going to do, so we haven't done this yet. So this is when we're going to determine the 5-number summary. So we're going to pull out the calculator. Whichever calculator you have, it's going to be the same for each calculator. Then we're going to do the exact same steps as if we were finding the mean and the standard deviation. It's the same exact steps, verbatim. So stat, edit, and you just start listing in all the data. 3.45, 0, and a 0. So I'm just going to start plugging in all of these. And a few of you can do this as well to make sure that I type this in right. 0.87, 0.52, 0.58, 2.33, 0.17. Looks like 18 values. So it's the exact same process as if you were finding the mean. So let's try to think back a little bit. We quit out of this, back to stat, go over to calc. It's one variable statistics. Now, hopefully you don't have anything next to the FREQ list in your calculator. I want to pull your calculator out and make sure of this, because if you have that, it's going to include a second column into your findings. So you just want something next to list if you have one of the more advanced calculators. If not, what you should get are these very familiar numbers on the screen, or these very familiar variables. In the 5-number summary, remember we defined it last time in class. The 5-number summary, it's smallest, the first quartile, the median, the third quartile, and the largest. And in the calculator, they tell us that actually one after another. What's that?
Like for mine, I have to delete the L2 for frequency list.
Yes, you have to delete L2 for frequency list, or it's going to mess up your results. I knew those zeros were going to be interesting. Our first quartile is our minimum. I don't know how I like that. One, two, three, four, 5 zeros. I guess that does make sense. Well, I guess we'll go with it. Actually, let's change this up a little bit. I'm going to get rid of one of these zeros because I want some unique numbers here. I'm going to go into the list. I'm going to delete one of the zeros. So I'll go to the second zero and I'll press DEL, just delete it entirely. I want to get something different than the minimum in the quartile being the same. Deleted one of those. So I deleted one of the zeros. So that's as if I went up to the data list and I just got rid of one of the zeros entirely. Let's see how that comes out. Okay, that's better. So I just got rid of one of the zeros from the data set. And now we get some numbers that are at least unique, which this is normally typical. Normally, it's pretty rare that it's pretty rare to have a minimum in first quartile unless there's a lot of skew in the data. So let's go ahead and write out the 5-number summary. The minimum is 0, which is smallest value. The first quartile is 0.115. The second quartile, which is the median, is 0.87. The third quartile, 3.195, and the maximum is 5.27. Okay, so now we're going to interpret the 5-number summary. So the 5-number summary, remember, when we stated the 5-number summary last time in class, I talked about how each value in the 5-number summary, the increments between them all contain 25% of the data approximately. So if we want to consider 25% of students watch blank hours or less of YouTube each day, then we need to figure out which number in the 5-number summary corresponds to being, well, larger than just 25% of the data. And so if we start off at the smallest one here, one leap brings us to 25%, so that's Q1. Q1 is the boundary. So this is 0.115, which is Q1. So it's 25% of students watch the first quartile or less. So at that point, Q1, 25% is less than Q1. And then it moves on with 50% is will watch a certain amount or less each day. And so with 50%, yeah, that would be Q2 because at the median, so at the median here, what would be less than the median? That would be 1 jump, 2 jumps, 25, 25, 50. So that's why this one is going to be 0.87, which is the median. And then 75%, I think you can see the pattern here. 75% watch blank or less hours on YouTube. That's Q3. That's the 3.195. And the reason why, so Q3, how many are less than that? 1, 2, 3. That's 25, 25, and 25, 75 in total. So that's interpreting the 5-number summary. So are there any questions up to the interpretation of this? If not, the interquartile range is the next thing. The interquartile range, we did define that up above. Interquartile range is the difference between the outer quartiles. That's it. It's a very easy computation. The calculator doesn't give it, but we can go one step further. I'll rewrite the formula down here. The interquartile range is denoted IQR, and it is equal to Q3 minus Q1. And this is a very important measure. This is a very important measure. Even though it's very simple to figure out, it's the range between the quartiles. And so Q3 we figured out was 3.195 minus Q1, which was 0.115. And so it's just a simple subtraction, 3.195 minus 0.115. This is 3.08. So now we get to interpret this result. So what does the interquartile range mean? So the interquartile range is how large of a region the middle 50% of observations fall within. The middle 50%. So this would be the expected value. This would be the equivalent of the one standard deviation from the mean if we were using the mean. This tells us an idea about how large the middle of the data is, how spread it is, because this is a measure of dispersion. So it's the middle 50%. The interquartile range always tells us the middle 50%. This is just always true. This is inherently true about the interquartile range. Has a range of, well, the number we found, 3.08. So we move on to the fences. So the interquartile range immediately helps us determine the lower and the upper fences. These fences, so I kind of mentioned this loosely in class last time, but the fences help us determine what the outliers are. So there's a lower and an upper fence, and if you have numbers that are outside of the fences, they're outliers by definition. So let's figure out what these boundaries are. So the lower and upper fence, I did define them above. The formulas are pretty straightforward. And I'll rewrite them here. The lower fence is equal to Q1 minus 1.5 times IQR, which are all values we know. These are all values we already know. So Q1 we found to be 0.115 minus 1.5 times the IQR, which we found to be 3.08. And similarly, I'll do the upper fence right below it, which is Q3 plus 1.5 times IQR. So that's 3.195 plus 1.5 times 3.0. So two computations, we can go ahead and figure both of those out. .115 minus 1.5 times 3.08. Negative 4.505. I know it's weird that we have a lower fence in the negatives when we're dealing with strictly positive numbers, but that just means we're not going to have an outlier on the lower end of this data set. Let's see about the upper limit. 3.195 plus 1.5 times 3.08. And so this is 7.815. So our lower fence is in the negatives, negative 4.505, and our upper fence is 7.815. And then part G immediately asks something in relation to this. Would 10 hours daily spent on YouTube, would that be an outlier? Answer is yes. Yes. 10 is larger than the upper fence. If you're larger than the upper fence or lower than the lower fence, you're an outlier by definition. So 10 is larger than the upper fence, which was 7.815. And then the final question, is the data skewed or symmetric? Is this data skewed or is it symmetric? At least intuitively, do you have any hunch? Think it's skewed, or do you think that's reasonably distributed? You think it's skewed? In which direction? Remember, it's skewed right if the tail's on the right, it's skewed left if the tail's on the left. So
It's skewed left.
if it's skewed left.
Yeah, because the zero values and the 0.87, 0.58, 0.58.
So
outweighs the 3.0.
the way you want to think about it, it's going to be skewed right, but I think your thought process is right. The highest concentration of values is not going to be the direction of your skew.
Okay.
It's all concentrated on the left, which means you're skewed right. Because on the right is going to be where your tail is at.
That's what I mean.
Yeah, so you had the right thought process, and students do that all the time. It's going to be skewed right, but that's just intuitive. On Help Me Solve This, they also mentioned another way of doing this, of looking for this. It's is Q3 minus Q2 approximate to Q2 minus Q1? For the median sense, this is something that they use as an indication for skew. So they ask this, and we can figure that out. And when I say Q2, I mean the median. They go back and forth between that notation, but Q2 is the median, so don't get too confused by that.
So that basically be what you ask yourself?
What's that?
That would be what you ask yourself? when you
Yes, until we get a visual representation, which we'll see later on in this section. So what is that? 3.195 minus the median, which was 0.87. 0.87. And then on the other side, that's 0.87 minus 0.115 it was ending up to be. 3.195 minus 0.87. It's 2.325. Is this approximate to 0.87 minus 0.115? 0.755. The answer is no. So are these two approximate? No. One is, of course, much larger than the other one. The smaller one is going to be the direction of the tail. Was that the larger one? Oh yeah, it is the larger one. The one with more dispersion at the end is going to be the direction of the tail. So Q3 minus Q2 is larger. implies skewed right. So that was one way I saw the book explain it when you're dealing with skew and median values. So notice that the mean and all the values, so the mean, the standard deviation, the variance and all that stuff, that is a completely different way of looking at data values. The median is completely different. There's no standard deviations when you're looking at the median. There's no mean when you're looking at the median. In fact, in this problem, it would have it's better that we did use the median as opposed to the mean, because the median is resistant to outliers. And there seemed to be some skew here. So the median would have been a much better choice than the mean. But other than that, does anyone have any questions before we move on? Okay. So let's keep going. So there's another data set, and we're going to ask a few questions about it. So I pulled up the last average day temperatures in Hammond between January 9th, 2021 and February 7th. And we're just going to do some 5-number summary statistics on it. So as you would imagine, I'm about to take all these values and plug them straight into the calculator. Or you can clear a list by going up to the list name, just pressing clear, enter. I'll go ahead and type in all these. For those of you not typing on a calculator, prepare to answer these next questions. Six, 65. 74, 7, 62, 1, 76, 73, 64, 57, 63, 67, 73, 55, 57, 61, 71, 30 values. And once you type all those in, we do the same exact thing we did before. And you should get values that, well, if you got a sample mean of 61.83, well, hopefully you all got that as well. Means we're all on the same track. And I'll wait until somebody else can confirm or deny these numbers. That's good, that's good. I'm gonna trust majority. So here's the numbers. And so we're gonna leave this off to the side for now. Leave that off to the side because they gave us some data values and they want the z-score. They want the z-score corresponding to 54 degrees. Now we had a formula for the z-score. The z-score for 54 degrees. Well, there's 2 forms of the formula depending on what we're using. And generally we use the sample standard deviation. So this would be the value minus the mean divided by the sample standard deviation. This was the formula that we defined a few pages ago in the notes. Which this implies that we need the sample mean and the standard deviation. That's what this is implying. So that's why you would be motivated to say, all right, let me figure out the mean and the sample standard deviation, which we can go ahead and figure out off to the side. So we'll call that 61.8, and the sample is 9.2. Remember, we're not using the population one, which is the Greek symbol, the sigma. We're using the one with S. That's 9.2. We generally use the sample standard deviation. So now we can put this all together. So the data value is 54 because that's what we want to find the z-score of. It says a forecast of 54 degrees minus whatever the mean was, 61.8, minus the standard deviation of 9.2. Let's figure out what that value is. 54 minus 61.8 divided by 9.2. And I get negative 0.8, just about. I'll just round it to negative 0.8. So we get a negative z-score. Can we even get a negative z-score? So we can. Negative 0.8. We can have a negative z-score. So what does this tell us? So it further goes on to have us interpret this and indicates that the data value is, well, when we think about z-score, the way we interpret it is if it's a negative value, then it's 0.8 standard deviations below the mean. So notice the negative, we interpret the negative as being below the mean. And this makes sense because the mean was 61.8 and our data value was 54. So a negative means that we are below the mean. How many are we below the mean? 0.8, the magnitude, not with the negative sign. And standard deviation always corresponds to the mean. From there, we can figure out the quartiles. And so they're not asking for the 5-number summary. They just want Q1, Q2, and Q3, which the calculator gives us in order. 6. Q2 is the median. They'll go back and forth between that notation, which is 62.5. Q3 is 70. And for one of my non-calculator guys, what's the interquartile range in this problem? What's that? Cool. Interquartile range is Q3 minus Q1. What does that number come out to be? I'll pass this off to one of you. What's that number? Well, I got the numbers right above. 70 minus 56 is 14. That's the interquartile range. It's that easy to find. So I guess we don't need the calculator. I have everything written here. We found the interquartile range. Let's go a little bit further. Determine the lower and the upper fences. The lower fence, I'll just rewrite the formula. That is Q1 minus 1.5 times the IQR. And right below that, I'll put the upper fence, which is Q3 plus 1.5 times the IQR. And again, this just gives the boundaries for which all the typical values lie in between. So let's see, that's 56 minus 1.5 times 14, 70 plus 1.5 times 14. Let's figure out these two values. 56 minus 1.5 times 14, it's 33.5. 70 plus 1.5 times 14 is 91. So the typical values in this data set, so basically what they're saying is a temperature less than 33.5 degrees or higher than 91 degrees for this, considering this data set, would be very unusual. So let's see, does this yield any outliers for us? Are there any values below 33.5 or above 91? And I wouldn't imagine there's any. This is pretty much January of Louisiana. I couldn't imagine. So no, there's no outliers. Every value falls within those boundaries. Now, give it a few months, we'll have plenty of outliers by this logic, plenty of over 91 degree days. But in this problem, there are no outliers. There are no data values that exceed 91 or fall below 33.5, and that's how you interpret that. Does anyone have any questions up to this point? And for some reason, my mind blanked. That's not 33.5. All right, so people in virtual, you were right. That's 35, my fault. Completely blinked on that one. I do that all the time. What did I do? I did times 15, not times 14. Okay, it happens. Okay, that's 35. But same idea. So are there anything that falls below 35? Things that get kind of close, but not really. So outliers, that still stands. Make sure you correct the lower fence to 35 in your notes. Does anyone have any questions up to this point? Okay, if not, we're going to look at box plots. And a box plot is simply a visual representation of a 5-number summary. If you took 105 last semester, you might remember box plots. It just illustrates the 5-number summary with a box, normally atop a number line. And I think there's a homework question that'll give you like one attempt, and it'll ask this bit of information. One of those two things, if you have a distribution that's skewed to the right, which means the tail's on the right, the median is left of center of the box. We'll see what that means momentarily. And right of center for a skewed left distribution. So one of those two is going to be a homework question. I think it only gives you one attempt, so there you go. And so from here, we're going to construct a box plot from, well, how many hours you all slept last night? So think about it. Give yourself a minute or so. Try to figure out how many hours you slept last night. Let's see. I fell asleep at 2. I woke up at 6:30. I work a lot.
I'm 4.5.
What's that?
I'm 4.5 too.
You're 4.5? Okay, well, two night owls. Okay.
I'm 4.5.
You're 4.5? Okay, this is it. I did not expect that to be the norm.
Mine is actually 4.5.
So you all went to bed at 2 o'clock and woke up at 6:30?
I went to bed at 12:30 and woke up at 5.
I was working on my car till like 1:30, and then I'm home.
Okay.
I'd use a fuel line instead of my vacuum line to get home. I'd be able to fix my car again today.
Well, this is interesting. We have, wait, you said 12:30 to 5:30?
Yeah, is that 4.5? No.
I want to get some different numbers. So I'm gonna call yours as 5.
Okay. Well, then you gotta erase a 4.5.
Well,
Oh, no,
my
you have
4.5, those two.
Okay.
What was yours? 6, all right, doing better. 5.5. Yeah, it doesn't have to be perfect, because I guess college, you don't sleep normally. Okay, virtual people, awesome. And I also gave up drinking coffee, so I've been extra, my mind has just not been happy with that decision. Try and play some racquetball later to get some energy. Maybe that'll help. Okay, let's write down the rest of these. So 796. Is that 498? I'm jealous of you people who are getting more than 8 hours of sleep. Six, 7, 2, 8. A 9 and a 7. 9 and a 7. Cool. All right, so we have some data to work with. All right, so find the 5-number summary. So you might know exactly what we're going to do. Pull up the calculator and figure out the 5-number summary. So we're doing all this to figure out the box plot. We need to know the 5-number summary. So that's why we are finding this first. So clear, enter. And someone else can type along with me to make sure that this comes out right. 4.5, 4.5, 4.5, 5, 6, 5.5, 7, 9, 6, 4, 9, 8, 6, 7, 2, 8, 9, 7. Okay, 18 data values. And provided I typed in everything correctly, 5-number summary that I get, okay, that's a perfect spread of data. Okay. Then it's 2. First quartile is 4.5. The median or the second quartile, either or. 6. 3 is 8, and the max is 9. Okay. And now we're going to draw a box plot of this. Now the box plot, there's a number line at the bottom, generally. Draw it about yay big. We always start with the minimum. So we'll call this 2 because that's the minimum. And from there, so normally we increment this in some consistent way. So I'm looking at the data and I'm thinking, let's do this by ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 5, 6, 7, 8, 9, 10. Could have easily went by 2s as well, but it doesn't matter. We start at the minimum and we draw a line all the way to where Q1 would be at, which is 4.5. So we drew a line from right above the number line, and I'm giving this a little bit of space from the minimum to the first quartile, which is 4.5. From the first quartile, that's when we're going to start drawing a box, and that box is going to stretch out to Q3, which is 8. If you're wondering what happens to the median, we'll get to that. And then at the end of the box, we're going to, from the middle, bring out a line that goes all the way to the maximum value. Now the median is going to be a straight line in the middle of the box that corresponds to where the median would go. The median is 6, so we're going to draw a line at 6. This is our box plot. So in order, This is the minimum. This is the first quartile. This is the median, the third quartile, and the max in order. And that's normally how it's notated, no matter what. And so we want to determine the shape. So this visualization, just like with using when we had frequency distribution graphs, this visualization helps us to determine the shape of the distribution. So is it symmetric, is it skewed left, or is it skewed right? And it seems as though here, it seems like there's a tail on the left end. What's that? So there's a few different indications here. Technically, this says for a distribution that is skewed right, the median is left of the center. And it seems like, well, we can definitely tell that the median is closer to the first quartile as opposed to the, actually, yeah, the median is slightly closer to the first quartile than the third quartile, slightly. So that means the median would be left of the center. It's to the left of the center, which now would say it's skewed right, but in a tail sense, it'd be skewed left. Now, personally, from what I remember, because I was getting a little tripped up on how to distinguish between these kind of contradicting ideas, and really what my math lab was recommending, what the book recommended, was the Q3 minus Q2, comparing that. Minus Q2 to Q2 minus Q1. So this was the way in which the book suggested trying to analyze this in your head. Now the differences here, it would be 2 to 1.5, and those are relatively close. Are they approximately close enough to consider this a symmetric distribution? That's relative. I don't know. Maybe in the sense of values that are so concentrated in such a small range, the answer would be no. And you would say that this is skewed to the right. Q3 minus Q2 is larger than Q2 minus Q1, which implies, let's see what we had before, skew to the right. So that's pretty interesting how this idea of skew differs from which metric we are using, which measure we are using. If we're using the suite of measurements that are the resistant measures, the 5-number summary, we have this specific way of measuring skewness. If it's the mean, so if we were looking at the mean here, that measures concentration of values. And so that may be something entirely different. Using the box plot will not give us a good indication of the mean. by any sense. The box plot does not tell us the frequency of values. There could be a, now it does give us some indication that the cluster of values are more towards the right, and then we would say that there's a tail on the left, but it's kind of this apples and oranges idea. And it gets a little messy. So to try to summarize all of that as best as I can, you want to compare the quartiles, the differences in the quartiles together. So it's kind of interesting. From a mean perspective, it would be skewed left. From a median perspective, it would be skewed right. So kind of interesting stuff. And we're going to also look at two box plots at the same time and compare them and see, well, how to analyze these. So the median of variable x. And notice this box plot has lines at the end. My typing software would not remove those lines at all. And it was 2 in the morning and I didn't feel like figuring it out. So I left them. But it means the same thing. Some books use that notation, but that would still be the minimum. This would still be the minimum. But in any case, the top box plot is x and the bottom one is y, irregardless. And the median of variable x. Now variable x, that's referring to the top box plot because there's an x to the left of it. And the question is, how do we figure out the median of that box plot? It's 70. And the reason why it's 70, this middle line is the median. Where does it drop down to? It's really close to 70. In fact, it's probably 70. My hand's just too shaky. But it's pretty much 70. And anytime you have to extrapolate information like that, or is it interpolate? One of those two, where you have to be very specific about trying to figure out where a line lies in an interval, that would be 70. So what about the third quartile of variable y? That's about 89. I think my math lab will give you a decent margin of error here. You could probably say 90 and it might even accept that. It looks like 89. It looks slightly to the left of 90. And remember, that says variable y, so that's why we're looking at the bottom box plot. And the final question, which variable has more dispersion? Yeah, I think from a visual perspective, it's obvious why this one has more dispersion. It's more spread out in every sense of the way. The inner box is spread out more. The min and the max are spread out more. Really, the dispersion. So box plot y has more dispersion. And this is because, not necessarily because the min and the max are, or the range of the values is larger. Really, this has to come down to the interquartile ranges. The interquartile range of y is larger than the interquartile range of x. And what I mean by that is this box is larger than that box. That's the indication for median-based problems. One box is bigger than the other. Does anyone have any questions about this? All right, well, that's let's just wrap it up there. That's all I have. So just keep in mind of the due dates. Group data is due tonight. Quiz is due Friday. You get those two out of the way. The quicker you get those out of the way, you get the whole Mardi Gras break. You don't have to worry about this class for the break. So should be a nice feeling.
We'll be out next week.
Yeah, we're going to be out next week. We're not meeting for this class next week. We don't have class Monday or Wednesday. It's Mardi Gras break. What's that? Yeah, go for it. But yeah, that's all I have. Have a good day.